All right, this lesson is about work, and here's your thought of the day: is homework really work? You can try to answer that by the end. In order for work to be done, by a physics definition, in order for work to be done, there's three conditions that have to be met. The first is that a force has to be exerted on an object, and the object has to be displaced. So there's the first two. And you can kind of imagine, here's an object, you can picture it's like a box or something, and I exert a force on an object. And if the object starts here and is displaced in this direction, then it looks like I'm doing work. At least the first two conditions are met. The third condition is the displacement has to be in the direction of some component of force. And what that means is, let's imagine the displacement is still this direction, same as we had above, but now the force is actually like on an angle, something like that. Is there a component of that force that's in the direction of the displacement? And you can say, sure. If we were to break that force up into components, you could kind of see that there's a component right there and a component here. So Fx and Fy. That x component does work. The equation for work then is given there. Work equals Ft cos theta. And the cosine of theta, if you look at this, here's the theta right here. This x component is actually the force times the cosine of theta. Okay, so what we're really seeing from this definition is the force and the cosine of theta is the x component times the displacement. It's really only the x component that does work. The y component does no work. Other than that, here's the equation. Work equals Ft cos theta. Work is, or W I guess is work. It's measured in joules. F is force measured in newtons. D is displacement. That's measured in meters. And then the theta that we're talking about here is the angle between vector force and vector displacement when they're tail to tail. In this little diagram here, if I was to draw them as if it was a free body diagram, if I was to draw the displacement there and the force right here, this angle right in there, that theta is this angle right here. So the angle is the angle between force and displacement when they're tail to tail. So let's try this out with a question, and we'll kind of see which forces do work and how much do they do. We can kind of see how to use this equation. So Mr. G's car runs out of gas. He asks and begs and whatever, pleads with students to help him push his car to the old gasoline store so he can get some more gas. Which students do work and how much does each do? Let's look at this. This is a top view of the car. Sometimes people ask, where's the force of gravity? Force of gravity is straight into the screen. If this is a top view and the normal force is coming straight out of the screen, those two forces cancel. But here we're looking at sort of a top view. These are all horizontal forces then, force 1, 2, 3, and 4. And let's see how to use this equation. Let's move over here. I'll leave the diagram up. And let's just sort of see student number 1. We know that, well, actually, before we do this, let's go in and say, for student number 1, let's just see where is the force. It's right here. I'll just draw the force. And where is the displacement? It's right here. When I put those two tail to tail, the angle kind of in between them right there, theta is just 0. Okay, so when I use my equation, work equals Ft cos theta. When we use this equation, we're just going to sub in the numbers. So the force, I don't worry about any vector like directions here. No positives or negatives, just sub in the number. So 1,000 newtons. The displacement, that's given up here, 10 meters. The angle between the two is 0. And cosine of 0 is equal to 1. Okay, so 1,000 times 10 times 1, the 1 doesn't really matter. We're going to get 10,000 joules. Student number 1 does do work. They do 1,000 joules. What about student number 2 over here? They're pushing in the opposite direction. Here, let's switch to blue. Can we see blue on blue? Let's try it. Student number 2. Now keep in mind their force is going to the left. Okay, so here's force 2. The displacement though is to the right. My diagram's not super great here, but this is supposed to be like a straight line. The angle right between those two is 180 degrees. Okay, so in this one, when we sub in, work equals Ft cos theta, again, when we use this equation, Forget about any directions. Okay, so no negatives on this 500. It's just going in as the number, magnitude only, 500. Displacement, still 10 meters. The car moves 10 meters. But the angle between them is 180 degrees. This cosine of 180 actually gives me -1. Okay, so when I go ahead and multiply this out, I'm going to get 5,000 joules, but it's a negative. Okay, so the work done by student number 2. First of all, do they do work? The question was kind of who does work and how much. Student number 2 does do work. They do negative work. We'll talk about what that means in a moment. Let's switch back. Let's go red this time. Keep it real fresh. Let's say student number 3. Do they do work? The force that they push with over here, this student number 3, the force that they push with is kind of straight south, I guess, if you want. The displacement, on the other hand, is straight east. Okay, so displacement's this way. The angle in here between them is 90 degrees. Okay, so when I use my equation, FD cos theta, we can say work is just 2,000 newtons. Again, I don't care about directions here, just sub in the number. Displacement is 10, sub in the number. This angle here, cosine of 90 degrees, this will take care of any direction stuff that we need to know. And cosine of 90 is 0. Okay, so it actually doesn't matter what force and displacement I sub in here. I'm just going to get 0. So no work. No work is done by student number 3. We'll put an exclamation mark. And let's see, they'll go back to orange, whoops, for this last one. Student number 4, where are they? Oh yeah, they're over here. So student number 4, the force is kind of coming up this way. Okay, and let's just keep in mind the dotted line here, our 30 degrees is out there. There's our force, force 4. But remember, the displacement is this way. The angle between them is not 30 degrees. The angle between them is actually this 60 degrees. Okay, so again, when I go ahead and sub into this equation, don't worry about any directions. Don't worry about any vector, directions, anything like that. We're just subbing in the numbers. Force 800, displacement 10. Cosine here is 60 degrees. And let's just work this out. I think cosine of 60 is 0.5, but let's just double check. Times 10 times cosine of 60. Do make sure you're in degree mode as well when you do this on your calculator. We're going to get 4,000 joules. Okay, so the original question, who does work? Student 1, so number 1, number 2, number 4 all do work. It's only student 3 that does no work. There is this difference in signs. So there's positive signs. I didn't write the positive signs. You don't need to, but just to make it clear, there's positive signs for student 4, for student number 1, that's positive work. If you do positive work, we're going to see this as we go through this unit. Work is a transfer of energy. It's how much energy did you give to the object. Okay, so student number 1 transfers energy to the object. They give the object some energy. Student 4, same thing. If it's positive work, they give the object energy. Student 2 does do work, but they do negative work. That means they're actually removing energy from the car. And we'll discuss that more as we get into energy, what that means, but that's what the signs here mean. So no directions given for work. A couple things to note here. Work is a scalar. So again, that's why there's no direction. Okay, so we don't say work is 4,000 joules east. That doesn't make sense. It's kind of like saying, this video is 3 minutes east long, or something like that. There's no direction for time. There's no direction for work, but it can be positive or negative. Okay, so work is a scalar. The units of work, if you think of that equation, right, FD cos theta, the force here is measured in newtons. The displacement here is measured in meters. Okay, so there's our Newton meters. And then work gives us an answer in, in joules. Okay, so 1 joule is 1 Newton meter. You can have negative work. We talked about that if you're removing energy from whatever you're doing the work on. Work is done by one object on another. In our example, we talked about how much work did student 1 do on the car? how much work did student 2 do on the car? It's done by one object on another object. You can talk about the net work. Okay, so we could say how much net work was done on the car, which sounds like your network or something, but how much net work, how much total work. In that case, you could say find the total force, or the net force, times displacement times cos theta. Okay, so we can do that. I'd say that's not the norm, but you could definitely do that as well. We didn't do that for our example, but you could find the net force, multiply by displacement, and times cos theta. Oh, and last thing. If I was to pull a wagon, so let's say here's a little wagon, and just imagine my force is going straight out this way. So I'll draw me, or a person over here. Let's see, can I make this look a little bit like a person pulling? Here we go. Imagine they're leaning back. They're actually touching the rope, but the person puts a force on the wagon. And remember, by Newton's third law, there's a reaction force back on the person. But imagine, as this person is pulling the wagon, they're moving this direction. They're moving kind of forwards or east. You could say the work done on the wagon, that force and this displacement are in the same direction. That would be positive work. So the person does positive work on the wagon. But you could also say the wagon puts a force on me. That force is this way. The reaction force is this way, but the displacement is this way. Remember, that's going to give us that cosine of 180 degrees. So let's say theta in here, 180 degrees. That's going to end up with negative work. So if I do positive work on the wagon must be doing negative work on me. We'll talk about that more, what that means when we get into energy. And last thing, we'll end with this. If I do a force versus displacement graph, and we get something like this, this isn't very common, but it does come up a little bit in our textbook. The area underneath that graph is work. So again, if you think of area kind of being like length times width, in our case, work, not force, work is equal to force times displacement. And I know that there's a little cos theta in here, but you can kind of think of this part of it right here. It looks a lot like length times width. That area in there is work. Okay, so if we were to go ahead and find this area, and when I say area underneath, just keep in mind that's actually between your line and the displacement axis, the x-axis. If this line carried on and sort of came down beneath the axis, okay, so something like this, the area that we're finding then is this area and then this area under here. Okay, so anytime we say area underneath, the line or underneath the curve or something like that, what we really mean is between the line and the x-axis, or in this case, our displacement axis. Doesn't come up too often, but you might see that in your textbook. And that's it. I'll let you decide if any of this is really work